We use AI all the time, right? And it feels, well, invisible, almost like magic. But what's really happening behind the screen? Well, it's not magic. It's a massive physical world of hardware and power. So today, we're going to pull back the curtain and look at the real, unseen energy cost of the AI we use every single day. So think about it. You ask an AI for a quick recipe or for help writing an email. It just pops up. It feels completely free, totally effortless. But is it? What's the real cost of getting that one single answer? Well, to find out, we have to go on a bit of a journey. From one tiny little chip all the way up to a computer that's basically the size of a city. All right, so to figure out that cost, we've got to build the engine first, at least, on paper. We're going to use OpenAI's GPT-4 as our example here. Now, these companies are super secretive about their hardware, but we can make some really good estimates to piece together just how huge this thing actually is. Okay, let's build this monster from the ground up. It all starts with one of these, an Nvidia A100 GPU. This thing is a total beast, and just one of them sucks down 400 watts of power. Now, you take 8 of those GPUs and you stick them together in what's called an HGX server. Suddenly, you're pulling up to 6 kilowatts. But here's the kicker. To train GPT-4, you don't need just one of these servers. No, you need about 3,125 of them. That's a grand total of 25,000 GPUs, all fired up and working together. So you've got this army of 25,000 GPUs. Great, but now what? Making them all work together is a whole other problem. It's a huge engineering challenge. You can't just flip a switch. This quote really nails it. It's like trying to get 25,000 chefs to cook one single meal all at the same time. It would be chaos, right? You need a plan. You need a system. So how do they pull it off? How do you tame all those GPUs? The secret is something called parallelism. It's this really clever, multi-layered strategy where you break the work down into smaller, coordinated chunks. Let's walk through the 3 key types they use to make something like GPT-4 even possible. Okay, layer 1. This is the smallest level. It's called Tensor parallelism. This all happens inside just one of those HGX servers. Remember, the 8 GPUs? Well, they're connected by this super fast protocol called NVLink. This lets all 8 of them team up to solve one giant math problem at the same time. It's basically a divide and conquer approach. It's what makes them so much faster together. Right, so that's how you get the 8 GPUs in one server to play nice. But what about the other 3,000 plus servers? How do you link all of them? That's the next layer, pipeline parallelism. And the best way to think about this is like a factory assembly line. See, GPT-4 is built with about 120 different layers, so they just break it up. One group of servers handles the first few layers, then passes the work to the next group for the next set of layers, and so on down the line. The data just flows right through. Okay, so get this. When you combine those first 2 layers, tensor and pipeline parallelism, it only takes about 120 GPUs to run one full version of the GPT-4 model. But hang on, we've got 25,000 GPUs. So what are the other 24,880 GPUs doing? Well, that's where the third and final layer comes in, data parallelism. This is where it gets crazy. They just copy-paste that entire 120 GPU assembly line hundreds of times over. Then each copy gets its own separate piece of the giant training data to work on. This is how they unleash the full power of that massive cluster. All right, we've built the machine. We've organized our 25,000 virtual chefs. So now it's time to see the bill. Just to remind you, this entire training process, with every server running flat out, took about 3 months, 90 days of nonstop work. So, what's the grand total? All that hardware running 24/7 for 3 straight months, chewed through an incredible 44 gigawatt hours of electricity. That's 44 times million kilowatt hours. It's such a huge number, it's kind of hard to even wrap your head around, so let's try to put that into perspective. So, that 44 gigawatt hours, that's enough electricity to power a city of 50,000 people for a whole month. Think about that. The power for an entire city for a month was used for one single training run of one single AI model. But here's the thing, that's not even the whole story, not by a long shot. Yeah, you'd think that training the model would be the hardest part, right? That once it's built, the heavy lifting is done. Well, here's the twist. The energy it takes just to run the model every day, to answer all of our questions, that process is called inference. That actually costs even more. Let's compare the numbers over the same 90-day window.
So on one side, you've got the training, 44 gigawatt hours, a one-time cost over 90 days. But look at the other side. Just serving its 700 million users, answering all our questions day in and day out, over those same 90 days, that consumes an estimated 67 gigawatt hours. I mean, that's insane, right? The ongoing day-to-day use is way more power hungry than the initial training.
Oh, and believe it or not, it actually gets worse. I mean, imagine the heat coming off 25,000 GPUs. It's immense. So for every single watt you spend on actually computing, you have to spend even more energy on cooling to stop the whole thing from, melting down. There's a metric for this. It's called PUE, or Power Usage Effectiveness. A pretty standard PUE is 1.2, which basically means you're burning an extra 20% of your total power bill just on AC. So let's factor that in. Let's add that 20% cooling tax to our numbers. The training cost, that jumps from 44 up to almost 53 gigawatt hours. And the cost of just running the thing every day, that goes from 67 all the way up to a mind-boggling 80 gigawatt hours. That is the real energy bill for just 3 months of GPT-4.
Okay, so when you see numbers like that for just one model, you start to zoom out and see the real story here. The big race in AI, it's not just about who has the smartest algorithm anymore. It's turning into a global gold rush for something much more basic: electricity. And the scale of this is it's hard to process. Just last year, in 2023, data centers were already using more than 4% of all electricity in the entire United States. But with this AI explosion, some people think that number could jump to almost 10% of the entire grid by 2030. We're talking about a massive strain on the system, and it's kicking off a new kind of arms race. And the big players are already making their moves. Look at this. OpenAI is apparently planning something called Stargate, a 5-gigawatt supercomputer. Elon Musk is buying up methane turbines for his own project. Meta is building its own natural gas power plants. I mean, think about that. These aren't just tech companies anymore. They are becoming full-blown energy companies. And this is where things get really interesting from a geopolitical standpoint. You've got two very different approaches. In the US, it's the private companies, the Metas and the Googles, who are driving this. But they have to fight through local pushback, regulations, permits. It can take years. Then you look at China. There, it's all state-driven. The government decides to build a massive new solar farm or nuclear plant, and it just happens. They can move at a speed that's almost impossible to compete with. Which brings us to the big question, really, the one that's going to define the future of all of this. In the global race for AI supremacy, who's going to win? Is it the team with the smartest algorithm and the cleverest code? Or is it just the one with the biggest power grid? The answer to that question is going to shape everything.